Okay, so before starting today's lecture, there are two announcements. First announcement is related with your project. In the last class, I said that by the end of this week, you will understand that what you have to do in your project. But unfortunately, I don't. I was not sure that Friday is a holiday or not. But now I know that tomorrow is a holiday, so but if I wait for next week, then it will be too late. So what I'll do, I'll upload two recorded video tomorrow. You don't watch it tomorrow because tomorrow is a holiday, so but watch it on the weekend and start working on your project from Monday. So for working on the project, you need to install a simulator, and then once you install the simulator, then the remaining steps will be discussed on the video. Even for the installing demo will be also shared with you. So you start working on your project from Monday. And yes, for project work you may need to do some extra work. Means whatever I'm discussing in this course may not be sufficient for this project, because there are extra marks for projects, right? So maybe you need to study some extra concepts, and maybe you need to study need to watch some extra videos. All these things may be required, so which is not included in your main course syllabus. So whoever will give more effort, then he will get more marks in the project. So the projects will be shared by tomorrow, and you start working from Monday. Otherwise it will be too late. This is the first point. Second point is your mid-sem papers are already corrected, so my TAs will share the answer key by today evening, and most probably by tomorrow morning they will share the all the marks. And after that, these TAs will arrange for some live session to clear your doubts and all. So everything will be managed by my TAs. So this is the second point. Yes, there are one more point, and that point is related with your assignment. So we have downloaded all the assignments, and assignment checking will start from next week. So next week again, TAs will give you slots, and in that slot you will present your assignments. Unfortunately, we have found many copy cases in assignment. At the beginning of this course, I strictly instructed you that not to involve in such activities. But unfortunately, we found 31 students copied from other students. So 31 plus those from where these students has copied. All of you will get zero in that particular question. For example, if question one, a student X copied it from student Y, and the question number one, then for question number one, both X and Y will get zero, and there will be no argument on it. So when the TAs will evaluate your answer script, at that time TA will also inform you that this question is copied, and they will give you zero. And if you think that this is not copied, then you can send a email to me for recheck. But you have to remember that if I recheck it and again I find copy case, then I'll give you negative marking, because I don't want to spend time on those who copied it, because I don't like this type of students. Because at the beginning I specifically mentioned that don't involve in this type of activity, but unfortunately you still did. 31 student copied out of 100 students. It's very huge number. So be ready for this strict action on assignment checking, and same thing will be done in project also, because I don't have any proper mechanism to detect this type of case in mid-sem exams. But I'll do the same thing in project as well as in assignment, and I'll not listen any justification if copy case is found. Okay, so I'll start my today's lecture. So last class I stopped on reducing the cache misses by, yeah, I was discussing about set associative cache memories. So first I'll go with the whiteboard and I'll start explaining set associative cache again. So sorry. So in last class, I discussed that a set associative cache look like a two-dimensional 2D array. Suppose there are so these are called sets. Suppose set number 0, 1, 2, 3. So there are four sets. Suppose here, and these are called V. So this cache is called four-way set associative cache. This is called four-way set associative cache. You have to remember this term. So if there are more number of ways, suppose instead of four there are 8 ways, then that cache will be called as 8-way set associative cache. So what is the property of set associative cache? Here you can say you can see there are four sets here. So a block will be mapped to a particular set. Suppose core is requesting for a block is called b1, and so block can be mapped to any of these sets. Suppose block is mapping to set number 3, then it means that this block b1 can be placed in any of these four positions. Which are the possible position? I'm making circles. So wherever I make a circle, in any of these positions this block b1 can be placed, but you cannot place b1 outside this set. Means you cannot place b1 in set number 0 or set number 1, even if those sets are empty. So if you compare it with the direct map cache, if you remember direct map cache, in direct map cache there was also sets like this, but there was only one way in direct map cache, right? So if the b1 is mapping here, then there is only one place for b1 in direct map cache. If you want to store, suppose there is another block b1, b2, b3, b4, all are mapping to same set, then in this case in direct map cache you can only place only one block out of this four block can present at a time in cache. But if you go to set associative cache and suppose b1, b2, b3, b4 all are mapping to same set, then you can place all of them in set number 3, b1, b2, b3, b4, all you can place in set. But after this, if you want to store more number of blocks, then you need to replace someone. That point I'll discuss again after some time. So here I'm only explaining the structure of set associative cache. Okay, so now in this diagram there are four ways. Suppose if I assume that the block size is 64 bytes, suppose, and then what will be the size of this set associative cache? Can we calculate the size? That how many sets are there? There are four sets. 4 into what is the size of each set? How many entry ways are there in each set? 4. And what is the size of each block? 64. So 4 into 4 into 64 byte. This is the size of this cache. 4, I hope you are understanding. First 4 is for number of set. How many sets are there? 4 sets. And in each set how what is the storage? This is the size of each set. So in each set you are storing 4 block. So because there are 4 way, so 4 into each block size is 64. So 4 into 4 into 64, this is the size of this cache. So now if I do some modification, what I'll do, instead of 4 ways, I'll make it 8-way associative, but I'll keep the size same. What is the difference between let us remove this cache? What is the difference between the top cache and bottom cache? Both are set associative cache, but the bottom one is 8-way associative cache, right? So now what will be the size of this cache? Size is still same. So there is how many sets are there? 2 set into how many ways there in each set? 8 into 64 byte. So you can see here size of the entire cache is still same, but there are two different structure possible. Here there are 4 ways and 4 set. Here there are, in the second diagram there are 8 ways but only 2 set. So if I go for more extreme case, then what I can do here, I can go for only one way and 16 sets. Suppose sorry, one set and 16 way. So in that case, there as I am not writing all the ways, assume there are 16 ways here. So in that case, the size of the third cache will be one set into 16 into 64 byte. Again, the cache size is same, but there are three different structures. And then another extreme case will be the direct map cache, right? In direct map cache, there will be one way in each set, but there are 16 sets here. Okay, so in that case, the uh, size is 16 into 1 into 64 byte. So you can see there are different combination possible, but all of this cache, there are four cache I have drawn here. All the cache size is same. So the size is fixed, right? But you can for same size of cache, you can design different structure of cache. This is 4 ways associative cache, 8 ways associative cache. This one is called direct map cache, and the last one here it's called fully associative cache. This is called fully associative cache. Why fully associative? Because here there is only one set. So what is the property of this cache? Here any block can be placed in any position because there is only one set. For example, if I go with b1, you don't need to check which set this b1 is mapping because there is only one set. So all the positions here, all the 16 positions that I'm showing here in fully associative cache, all the 16 positions are open for any block. This is the property of fully associative cache. And in direct map cache, you already know the property. There is only one position for each block, right? This is called direct map cache. And in set associative cache is the combination. It's the intermediate of direct map cache and fully associative cache. If we one extreme of set associative cache is fully associative cache, and another extreme of set associative cache is called direct map cache. So set associative cache is the intermediate cache structure, and this is the most well-known structure because I most of the time from this point, whatever I will discuss on cache memory in this course, most of the time we'll only concentrate on set associative cache. So in this lecture, I'll spend some time on explaining the behavior of set associative cache. First, you need to understand in a very top level that set associative cache looks like a 2D array. I hope you know the concept of 2D array, right? So if you just concentrate on this set associative cache, it looks like a 2D array, right? So rows are called set, ways are called column. And in each entry here, like in 2D array, we call this as entry, right? So each entry is storing a particular block. Now, what a block store, if I magnify this block, that I think I have already explained that what we store in block, first we store data, obviously the actual block content, right? That is called data. The actual block will be stored, that we actually fetch from main memory. Then we store the tag, and with that some bit, that is the valid bit, and as I said, maybe we need to store a dirty bit also. So all these things are stored in each block. So out of this, data is the main block that we fetch from main memory to the cache, and then tag, and then a valid bit, and then a dirty bit. So all this, so all the entries here will store this information. So whenever we say block size is 64 byte, you have to understand that we don't consider this normally. I think that that part I also explained. But every time whenever we say about block size, we just say about this part, 64 byte. We normally don't consider this, but yes. So even based on 64 byte, if I say that this is the size of the cache, but actually the size of the cache is the size is little bigger because we are not considering the tag part and some other valid part. So some other bits. So this part is called actually metadata of a cache block. So metadata part is also not it's not a negligible storage, but still we don't consider it here. Okay, so I hope you understood the concept of set associative cache, and what is the difference between set associative and fully associative and direct map cache. So now, what is the advantage of each set? So if you go with direct map cache, the easiest the main advantage there is it is easy to search. I'll explain it again why it is easy to search. Search time will be less. This point I'll again explain. So here the disadvantage is there will be more conflicts because for a particular block there is only one location. There is only one location, right? So there will be more conflicts. If you go to fully associative cache, there will be no conflict. So when I'll say conflict means suppose first core request for block b1, and b1 you placed here in direct map cache. Okay, after this core is requesting for b2, and b2 is also mapping in this set. So you have to remove b1, but at that time there are space available in this case. Assume that these two positions were empty, but even after that you are not allowed to store b2 there, and you have to replace b1, and then in place of b1 you have to place b2. That is called conflict. Okay, and in so if you go with fully associative cache here, there will be no conflict. Means b1, b2, b3 you can place in any position, there will be no conflict. Means conflict there is a difference between conflict and capacity. Means if the cache is full, then obviously you need to remove something, right? That is different point. But here what was happening in direct map cache, you need to replace something even when the cache is empty. I mean, cache is not full. So that was called conflict. So if you go to fully associative cache, there will be no conflict. You can place any block in any position. Obviously, when the cache will be full, and then after that, if one more block is requested by the core, in that case, you need to replace one block. That is called capacity miss. But the cache will be full. Before the cache is completely full, you no need to replace anything. So there will be no conflict miss. And in direct map cache, there will be a very high conflict miss. And in set associative cache, conflict miss will be intermediate, means it is less than direct map cache. Sorry, yeah, conflict will be less than direct map, but more than fully associative cache. So if you go with four-way set associative cache and conflict miss is suppose 10%, then if you go to eight-way set associative cache, then the conflict miss will degrade. So conflict miss may be here suppose 5%. If you go to 16-way set associative cache here, then there will be no, because 16-way means this cache will become fully associative. The conflict miss will become 0%. So you have to understand all these things. And when I'll give you the project, I am in that project, I'll give you a software, right? I'll give you a simulation tool. In that simulation tool, you can do this type of experiment by your own also. That if my cache size is fixed, but my associativity is 4, then what are the conflict misses? If associativity is 8, what are the conflict misses? You can do this type of experiment by your own. So I hope the concept of set associative cache, fully associative, and direct map, the basic upper level concept is clear. So the main property here is in set associative cache, from this point I'll mainly concentrate on set associative. So in set associative cache, first of all, a set is being fixed for a particular block, and the block can be placed in any of the ways available in this set, but I cannot place it outside the set. Okay, so this is the main point of set associative cache. Now let us go to the book, and quickly I'll scroll down and I'll see how see they've explained here fully associative cache. I'm just scrolling it because I think I've already explained it. I'll not discuss this diagram. I'll advise you to read it by yourself. You'll easily understand it. So see, there are they have also explained different. This is direct map cache. Sorry, this is direct map cache. This is a two-way set associative cache. Why they are saying two-way? Because this is one block, tag plus data one block. This is another block, tag plus data another block. So this is four-way set associative cache. They have not shown here the other metadata like valid bit and data bit, but those are also important, right? So this is two-way set associative cache, four-way set associative cache. It is eight-way set associative cache like this. And if the size is fixed, because this eight-way set associative cache becomes fully associative, because the moment you can see here there is only one set exists, then it's a fully associative set. Okay, so this up to this part I've cleared. Now one more important point that I'll explain now. So if this is your set associative cache and there are multiple sets here, suppose there are 1024 sets here. Total number of set in this size is 1024, and ways are 4 again. So this is a 4-way set associative cache. Okay, so how to suppose now a core is requesting for a block B1. Okay, and this is the address of B1. This is a 64-bit address of B1. We know that there will be some bit here for offset, and there is some this part is called tag. So what is this part? The intermediate part is called index, right? So in case of direct map cache, we know that this, based on this, we go to a set. The same thing here, but you can see here how many sets are there. 1024 set. So to uniquely identify a set, how many bits do we need? We need 10 bits, right? So and so assume that block size is 64. So if block size is 64, then we need 6 bit for 64, right? So first 6 bit is for offset, next 10 bit is for set index, next 10 bits will be for set index, and remaining bits are for tag. Okay, so suppose this is the address of B1. So every time whenever the core will request for a block, then what is happening, first from this 64-bit address we'll find out this 10 bit, and based on this 10 bit, first the set will be decided. Okay, so if this 10-bit values are suppose 0 0 0 0 0, I'm not writing all the 10 bits, I'm just writing last few bits. Suppose all are 0 0 0 and last is 0 1 0. So if all are 0 0 0 0 here, then so it is representing set number 2, right? So set number 0 1, this is 2. So the block is mapping in this set. So in this way you can find out the set, so based on the set index. So this policy is almost same as a direct map cache, but what we said in case of direct map cache, if you remember, we said that you can find out a set using this formula: block number and then mod, block number mod number of blocks, number of blocks in cache, number of blocks total number of blocks in cache. So total number of blocks means 1 2 3 4 5 6 7 8. Like, I'll go to the book and I'll explain it. I think this is explained in book. Yeah, if you go here, this was the formula to find out the set index in a direct map cache, right? Block number and the number of blocks in the cache. So if this was the this is your direct map cache, then you have to understand that the number of blocks in the cache and number of set in the cache is the same thing for direct map cache, right? Because in each set there is only one block you can place. So number of block in the cache, and here if you see number of set in the cache, these two are same thing for direct map cache. So here in set associative cache also, the formula is same actually. Here also, this is the formula for set associative cache. This is the block number modulo number of set in the cache. So I think actually the things are same, because in case of direct map cache, number of blocks and number of set are same thing. So the beats that I said is that if there are 1024 set, then you can set this 10 bit, and based on this 10 bit you will find out the set index. This is the correct, this is one way. Another way you can say, in mathematically you can say that block number mod number of set, then also you'll find this. Both are same thing actually. Don't think that there are two different things. Both are same thing. So I hope the mapping policy is clear. So if the mapping policy is clear, then let us go again to the book and scroll the book down. You read all these things, it will be easily understandable for you. So I'm not explaining all these things. I'll directly go to a diagram. If I go to this diagram, then you'll understand that how you search in set associative cache. Because if you remember, I explained already that how you can search in a direct map cache, right? In last class I've shown you some diagram also, that how the tag that is stored in the cache and the tag of the incoming request will be compared, right? All these things I've explained. So here also the same thing. So every entry here is a block, right? So here we'll store the data and tag both. Just 1 minute. Oh, it is not charging. Yeah, tag and data both. So suppose there is a block. Suppose the core is requesting for a block. Suppose D1, this is a block, and this block is mapping in first set here. So you have to you don't know that if this block is present in cache or not. So if the core is requesting for a block D1, the first thing is we will search the block in the set associative cache, and then the result will be either hit or miss. So how to search? To search the block, first we will fix the set. So if assume that based on the set index, D1 is mapping in first set. Okay, so once the D1 is mapping in the first set, there are 4 positions, right? This and all the positions. So there is a tag here. Assume there is one more tag here. There is a tag. There will be tag here. There will be 4 tags. So all these 4 tag you have to compare with the tag of this D1. This D1 as a tag. So this tag will be compared with all these 4 tags here. And if any of this tag is matching, then it's a hit, and the corresponding data will be sent to the cache, to the processor. So the same diagram they have shown here. So here you can see it's a 4-way associative cache. So this is one block actually. You can one block. So this is way 1, way 2, way 3, and way 4. The same thing here. So the 4-way associative cache, and here you can say these are set 1 0 1 2 3 4 5 6. There are 6 set and 4 ways, and each way has v tag and data. So suppose this is the address of, suppose this is D1. So they have divided it. This part is offset part. This is offset, and then after this, this part is actually set index. So they are using 8-bit of set index, right? They're saying 8-bit. Why 8-bit? Because I think they assume there should be more number of sets here if the 8-bit is there. But I think they have shown less. No. I think see, they have also shown like the zero in set index are 0, 1, 2, and then 253, 254, 255. So you have to understand that there are 255, 256 sets are there, not 8 set. They have just assumed that they have not shown all the sets. So if you have 256 set, then you need 8-bit for set index. So they have correctly said here that there are 8-bit. So based on this 8-bit, first a set will be decided. So assume that this is the set where the block D1 is mapping. Once this is fixed, then this entire set you can see, let me change the color. So the entire set that you can see here, this entire set, so there are 4 tags here. This will be tag 1, tag 2, this is tag 3, and this is suppose tag 4. All these tag will be available here automatically, and it will be here in this comparator. This is the comparator. And the incoming tag, you can see this is the incoming tag. I'm changing the color. So this is your incoming tag. So this, you can see the incoming tag is giving as an input to all this comparator. So it means that all the 4 position of this set, there are 4 positions, 4 ways in this set, right? So all the 4 tag in this set are simultaneously comparing by 4 comparator. This is comparator 1, comparator 2, comparator 3, and comparator 4. So there are 4 comparator, and so these 4 comparator are simultaneously comparing the 4 tags with the incoming tag. And if any of them is hit, then you'll get a hit here, because this is a OR gate. I hope you know what is the purpose of OR gate. Means any of them is hit, then it will go for a hit. And it's not possible that there will be 2 tag match, because hit in 2 position is not possible. So there will be only 1 position. Either all the input of this OR gate will be 0. In that case, it will be a miss. And if any of them is 1, then it will be a hit. And you can see what is happening with the data path. So see, the data is also coming from all the 4 locations here. All the 4 location data is coming, and there is a multiplexer here. And in this multiplexer, all these tag comparison results are going. And out of this, only one can be the thing will be out of this 4 input that is going to this multiplexer. Only at max one can be at least only one of this can be high, other will be 0, like this, or all will be 0 0. All will be 0 0 means it's a miss, and so nothing will come out. But if it's a hit, then the corresponding location will be selected, and the corresponding data will come out from this location. And obviously there will be one more multiplexer here for the offset part that I have explained, and then the specific word will be sent to the core. So this is how a search happens in set associative cache. Okay, here there are, if it's a 4-way set associative cache, then you need 4 comparator, right? So if it is a 8-way set associative cache, then you need 8 comparators, right? So this is a limitation. When I discussed about direct map cache, if you remember, so I'll explain from here only. This was our direct map cache, right? In direct map cache, there is only 1 way per set. So it means you need only 1 comparator in case of direct map cache. That's why searching is fast there, because the while here, if you go with fully associative cache, then see there is a long wire required, right? And also you need a bigger circuit, because you need 4 hardware and some additional OR gates, and multiplexers are also required. Those will be not required if you go with direct map cache. That's why in direct map cache, the complexity is less, search time is less, because there is only 1 comparator. This is the, I'm only saying our advantage. You already know the disadvantage of direct map cache. If you go to set associative cache, suppose it's a 4-way set associative cache, then you can see from the diagram the hardware required for it. If you increase the associativity from 4 to 8, then the hardware overhead will be double. And if you increase it from 8 to 16, then again the hardware overhead will be double from the 8-way associative cache. Because if it is 4-way or it is n-way set associative cache, all the ways present in that particular set will be compared simultaneously, and you need this much comparator. Okay, so that this is the disadvantage of set associative cache. So that's why if you keep on increasing the associativity like 4 to 8 and from 8 to 16, then there will be hardware overhead. Search time will also increase. Why search time will increase? Because of this internal wire length, because there will be long wires is required to connect these comparators and all. So search time will increase. And I hope now you already understood the disadvantage of fully associative cache, right? So if you have, so just check, assume this particular cache. It is, there are 4 ways, right, at this moment, and 256 set. If you want to convert this particular cache into a fully associative cache, then you can understand that how much comparator will be required, because from 256 there will be only one set and all the ways will be merged in one set, right? So this much, I think 4 into 256 number of comparators will be required, and you can imagine the complexity of the searching mechanism and all. So in that case you will understand that fully associative cache is very expensive in terms of searching. Okay, but you know the advantage of fully associative cache. If we can assume that no, there is a magic hardware, a magic hardware exists, and based on that magic hardware, fully associative cache you can search in same as a 4-way associative cache. For example, suppose this is a fully associative cache. There are a lot of comparator required, but we'll assume that the search time is same as the cache that I have shown here. Means search time of this cache is same with this cache. If this is the case, then you know the advantage of fully associative cache. In fully associative cache, there will be no conflict misses, right? So you can fully utilize the cache. But the disadvantage is this type of search is not possible, right? So in real physical design, if you go with a fully associative cache, there will be huge search time. That's why people don't go with fully associative cache normally. Fully associative cache are only used for some small buffers and all. And then why we are not going with direct map cache? Because if you go with direct map cache, then there is only one comparator, hardware overhead is so less. Why we are not going? Because of the high conflicts. High conflicts, you cannot utilize the complete cache properly. That's why direct map cache is also not a good option. Then the intermediate is set associative cache. So now set associative cache means how many ways? 2-way, 4-way, 8-way, 16-way. That depends on the design and all. So all these things we'll discuss in this course, but here you have to understand that the hardware overhead wise set associative cache is the intermediate thing. Cache conflict means wise also set associative cache the intermediate choice, and that's why most of the cache memory, modern cache memories, are actually set associative. They are not fully associative, not directly mapped. Okay, so with this explanation, I'm skipping all this here, but you have to understand this concept. You have, what I'm advising, you read all the section here line by line, and if you find any of the concept written here is not clear, then you can always ask me. Now I'll explain one more interesting point of set associative cache. So from this point onward, most of my discussion will be based on set associative cache. Again, I'll take a simple 4-way set associative cache, and suppose core is requesting for some block B1 to Bn. Suppose there are all these blocks are requesting by the core, and assume that all the blocks are mapping to a particular set here, that is set number 1 here. So B1, B2, B3, B4 set is now full. After this, when core will request for B5, suppose now core has requested for B5, and I already said that all these blocks are mapping to the set number 1, then what will happen? Set is full now, right? So in that case, you have to replace something, and in that position, you have to place B. Now the question is which block you have to replace. There are 4 blocks, B1, any of them you can replace. You can replace B4, and in place of B4, you can you can place B5, or you can replace B1 also, and you can, in place of B1, you can place B5. So which one you have to replace? This is called replacement policy of a cache, and a well-known replacement policy is called LRU, least recently used. Least recently used means out of these 4, B1, B2, B4, which one is the oldest block? Oldest means which the block which is accessed in the past, that will be removed. So assume that the way core requested, right? Core requested first B1, then B2, then B3, B4, and then now core is requesting B5. If we go in this sequence, then you can say that B1 is the oldest block, right? So in that case, we will remove B1, and in place of B1, we'll place B5. But that cannot be that may not be true every time. I'll give you another example. So now assume that the sequence in which the core is requesting is this. First code requested for B1, then code requested for B2, then code requested for B3. After B3, code again requested for B1. Possible, right? Code is requesting, and according to temporal locality, if it is requesting for B1 now, in near future it can again request B1. So now, and after this, there is code again requested for B2, and then it is requesting for B5. If this, sorry, now after this it is requesting for B4, and after B4 it is requesting B5. In this case, what do you think, which block can be replaced? Any answer? This is the sequence now: B1, B2, B3, B1, B2, B4, B5. So what do you think, which block should replace to place B1, B5 in the cache? Any answer? B3. Yes, correct, B3, because in that in this scenario, B3 is the oldest block. So this is called replacement policy, and at this moment the replacement policy that I am explaining is called LRU, least recently used. Instead of this, we can also go for a replacement policy like random. If the replacement policy is random, then I can randomly select any of this block, any of this four to replace, and in that position I can place B5. So this replacement policy is a huge area of research in computer architecture. Don't just think that it is very simple. Yes, LRU replacement policy is very simple, but there are disadvantages of LRU policy also. And from starting from 2001, now it is 2022. In this so many years, there are a lot of research already happened in this area, but it is still an open area. And I'll not explain why it is still an open area of research today, but I think the lecture that I'll record tomorrow, in that lecture, I'll explain all these things, that why still improvements are possible in this area in replacement policy. It looks simple, right? That I just need to replace some block, but it's a challenging thing to select a best candidate to replace. And the disadvantage of LRU replacement policy and all, I'll explain in next lecture. In fact, we'll spend at least two, three more lecture on replacement policy, because I want to cover replacement policy in more detail. But today I'm just explaining you what is replacement policy and why it is required for site associative cache. Okay, so replacement policy ho gaya. And then reducing the miss penalty using multi-level caches. So multi-level caches is explained in this section. So multi-level caches, if you want to understand the why multi-level caches is required. So in the modern day, what happens is, if this is the core, then till now what I said, this is cache memory and this is your main memory, right? That I have explained so far. This is your main memory and this is your cache memory and this is your core. This is I've explained, right? But if you remember the data path diagram that we have used pre-midsem, in that data path diagram, there is the instruction memory, there is a data memory, right? So during the fetch time, we go to instruction memory, and during the mem stage, we go to the data memory. So that in that case, if you think that your data memory, that is actually the L1 cache, that is the cache memory. So in that, if that cache memory is very big, because if that cache memory is big, then obviously search time will increase. Just now we have checked, right? If your cache is big or the associativity is higher, then your search time will increase. So you cannot put a big size of data memory, right? So this was your instruction memory, if you remember, and this side there was a data memory. These cache, you cannot design a much bigger cache, because if you go with bigger cache, then their hit time, the access time will increase. If the access time is increased, then hit time will increase, and hit time increasing means this is directly impacting the pipeline stages. So it means that these data memory and instruction memory cannot be bigger. It should be small enough. It should be small. So, but the another direction is, if you go for a bigger size of cache memory, then you can reduce the number of misses, right? If you have a bigger size of cache memory, then there will be you can store a lot of data in this case, so you no need to go in main memory multiple times. So there are two opposite purpose of cache memory, right? The first, you can see, if you increase the cache size, then the hit time will increase, and if hit time will increase, then the mem stage and the fetch stage, these two stage time, more time is requiring, right? So that is the problem. And if you, to reduce this problem, if you go with small size cache, then the another problem is, if you go with small size cache, then it will increase the number of misses. So that is again against the using of cache memory, because we are using cache memory to reduce the number of misses. So in that direction, it is saying that no, go for a bigger size of cache. So there is a problem here. So that's why to resolve this problem, what people do, people go with multi-level of cache. The first level of cache is very small. So that's why I say this is suppose L1 cache. So there are two parts normally: L1I cache, that is the instruction cache, and L1D cache. So L1I and D both are suppose 32 kb, 32 kb. And even in modern processor, they are not more than 64 kbs. L1 cache are very small. Why they are so small? Because here we are trying to reduce the hit time. Okay, and then there will be suppose there are one more level of cache. This is a bigger cache. This is L2 cache. Okay, and maybe assume that after this there are one more level of cache. This is L3 cache, and all this are inside your processor. Okay, and this is main memory, this is outside the processor. So that's why we go for multi-level of caches. So multi-level of caches means if we go with this cache L3, normally we call it as last level cache, LLC. Remember this term LLC, it's called last level cache. So in last level cache, our main goal is to just increase the capacity. If we increase the capacity, it will reduce the miss. So in last level cache, our main goal here is to reduce the miss. That's why the capacity is higher. But if you go for a bigger size cache, then access time of L3 is more. So here access time means first you will if you will search in the cache, right, whether it's a hit or miss. If there is a hit, then you will return it from cache, that is fine. But that time is called access time. After accessing the cache, then only you will realize that it's a hit or miss, right? So if your cache is larger, then your access time will be also larger. So in that case, hit time is increasing. So here you can see hit time is very less in L1, but capacity is small. So you will face more misses, but those misses will be covered up by L2. It is an intermediate one. But even if there are some more misses in L2, then there is a even bigger cache available, that is called LLC, where the more number of misses will be covered. So more, you'll get more hits in cache. So even if you go with multiple levels here, so you can say that okay, if there is a miss in L1 and L2, then I have to go to L3. Then what is the advantage? L3 is the bigger cache, and also I have to travel from L1 to L1, L2, and then L3. So what is the advantage? Advantage is, even if you are going with LLC, then also there will be a huge difference between LLC hit and main memory access. There will be huge difference. This difference will be, even you can say 100x, 100 time difference is still exists. So that's why multi-level cache is people go with multi-level cache. All the modern processor has multiple level of cache memories. L1, L2, L3 are very common. Three level cache is very common, and the last level is called LLC. You have to understand this. So I think before midsem in one lecture I have explained that here you can see I have considered only one core. If instead of one core there are multiple cores, which is very common nowadays, right? Dual core, quad core, octa core processors are very common. So if there are multiple core exist, then how cache memories are distributed? I think that I have taken one lecture before midsem. You just revise that lecture, because that lecture will be important for your project work also. Okay, so I think the basics of multi-level cache I've explained here. You read this section, you will understand it. There is one concept of multi-level cache. It's called inclusive cache and exclusive cache. That point I'll not explain now. I'll explain after 2-3 lectures, because I don't have time today. Or maybe I'll explain the inclusive cache, because I think if I start from this graph, so there are some very interesting concept mentioned from this point here. But if I start from this point, I think I cannot explain everything written here. See, I have to explain till this point. Everything mentioned here are very important, very interesting, but I think I don't have time to explain. So what I can do, let us explain two interesting concepts which is not written in this book, but maybe it is written, I don't know. But so far whatever I covered, it is not mentioned. Maybe it will be mentioned after at the end of this chapter, but these points will be important, so you have to note it down. So to explain this, I'll go with two level of cache. Suppose this is your this is C1, this is suppose L1, and there is one more level of cache, it is called L2. Okay, and I'll go with only two level of cache. So here LLC and L2 are same thing. I hope you remember what is called LLC. LLC is last level cache, right? So here L2 is your LLC, and there is a main memory here. This is your main memory. So now suppose if core is requesting for a block called A. So first time when core requests for block A is not in L1. Okay, so we'll go to L2. A is not in L2, so we'll go to main memory and assume that, and from main memory the block will be first moved to L2, right? So I'll put block A here, and then I'll move from A will be moved from here to here also, and consider all the cache are set associative now. Okay, so this is called A, and after some time if core request for B, then same thing will happen. First we'll move B here, and then a copy of B will be moved here, and this thing will continue. Okay, and after suppose after some time a core is requested for C and D, then same thing will happen here for C and D. But it may be possible that associativity of L2 is higher than L1. So here assume that associativity is high. After some time, now at this point, if core is request for a block called X, then what will happen? See, there is no place to store X in L1. Assume all the blocks are mapping in the same set. So I have to replace one. So if LRU policy followed, then I'll replace X, replace A, and I'll store X here. But that is not the case here, right? In L2, you can place the X here because you have position for L2 here. So this design is called inclusive cache. Inclusive cache means there are two cache here, right? L1 and L2. But the content of L1 is actually a subset of content of L2. Means whatever content that is available in L1, they are also present in L2, right? So this is called inclusive cache. First, you fetch a block from main memory, you place it in L2, and then a copy will be moved to C1, right? So you can see that for X, B, C, D, all the content of L1 are also present in L2. Now, if C1 is requesting for a block called Y, then what will happen? See, in L1, there is no place for Y, so we have to remove a block from L1, right? So assume that we'll remove B, and in this position we'll place Y. Okay, but to place Y in L2, there is, suppose there is also still a position left here, so I'll place it here. But again, it's an inclusive cache. Why? Because L1 is a subset of L2. This is called inclusive cache. Another cache is called exclusive cache, because people may ask this, sir, why we need to store these X, Y, C, and D in both L1 and L2? We are wasting the cache memory, isn't it? Because L1 is also cache, L2 is also cache, and this is your chip, right? This is your chip. This is called on cache memories are called on chip memories. So this either the block is in L1 and L2, this is in the processor chip, and this memory is very far, right? This is off chip. So why you are wasting the cache memory? Means why you are placing X, Y, C, and D in two place? We don't want to place them in two cache memory. If C1 is if they are available in L1, then simply remove them from L2. So in that case, we'll remove X, Y, C, D from cache L2. Why? If you do this, then you are getting more capacity of cache, because you can store more block, because now you can see in L2 there are some position empty, right? So you can store more blocks here, so you can better utilize the cache memory. Because if only one copy is enough, right? X is still present in cache, Y is still present in cache, it is in L1. But this design is called exclusive cache. Why it is exclusive? Because the content that is stored in L1 and the content that is stored in L2 are, they're completely separate, they're distinct. This is called exclusive. Okay, so here in today's lecture, these 2 points you have to understand: what is called inclusive cache, what is called exclusive cache. I may ask these questions in future. Now coming to the advantage and disadvantage of inclusive and exclusive. One advantage of exclusive, I've already explained here, right? What is the advantage? There are some disadvantage of inclusive cache also. So both inclusive and exclusive, there are advantage and disadvantage, but those I'll not discuss today. Those I'll discuss later, because I think before that I need to cover some more concepts. But at least from this point, in next lecture I'll directly use these two terms, inclusive, exclusive. You should understand what I am saying. Okay, first point. Second point, I may use this term called LLC. You have to understand what is LLC, why I'm using this term LLC. You have to understand what is called set associative cache, right? I have already explained it, what is called set associative cache. So this small thing you should know. And with this I'll stop here, because it is already, I think, 3. And so I'll wait for your question for 2-3 minutes. If you have any question, you can ask now. Okay, so if you don't have any question that then okay, sir, the project is done. No, no, it's a team basis. So I think uh, there are 100 students, right? So the team, each team can should each team can have five members, because I don't want more. So I think I have I mentioned it, right, that the group size I have mentioned. If I'll check my document that I've shared in my lecture one, I forgot. I think the group size I have already mentioned. If it is not mentioned, then I'll share it in Google Classroom today by the evening. That what should be the group size. In exclusive cache policy, when a block is requested, it is it first search in L1 and then L2, or for every block it is fixed that it will be in L1 or L2? No, it is not fixed. You don't know. You only know that there are two possibilities, right? If code is requesting for a block, the block will be in cache, or block will not be in cache. If block is not in cache, you will go to main memory. And then the second point is the block in cache. If the block is in cache, then also there are now two options, in which case L1 or L2. So in that case, searching will be in same process. First they will search in L1. If the block is not in L1, then search will be in L2, because nobody knows, right, then where the block can be present. uh, okay, so start working on your project. I'll share recorded videos tomorrow, so watch them in the weekend, and from Monday you start working. And as I said, in project you may need to do something extra which I'm not covering in this course. You have to do something by your own also. I'll just give you some lecture videos which I may not explain properly in this course. You have to understand those lecture video, and based on this you have to implement some task. Okay, so if you don't have any other questions, then I'll stop the lecture here, because it is already 3. So let me stop the recording, and if you want, you can leave now.